Hello there, my dear physics learners. You're very welcome to the lecture number 2 of the physics lecture series by your very own personal physics tutor, Dr. Rima McMullen. That would be me. In today's lecture, we are going to discuss a rather easy yet very important topic of physics, that is dimensional analysis. However, before I get started with today's lecture, I would urge to you to get your paper and pencil ready so you can work along my side, you can take notes, you can solve problems, because until you do these things, you're not going to gain the fluency and the confidence that you need to master physics. Now, I'm sure that you have heard that physics kind of has a reputation of being hard. I would admit that this is not the most straightforward subject, but I promise to you that if you work alongside me, if you attend all these lectures and you solve these problems, you take your notes and you work diligently, and if you have any questions, you ask me in the comment section, you might find out that physics isn't as bad as they make it sound like. Who knows, you may even fall in love with the subject. All right, with that, I hope that by now you have your paper and pencil ready. All right, so let's start this class by listing the three base, that is the fundamental physical quantities in mechanics. Now, we went over that in lecture number 1. So let's do one thing. I will list those physical quantities on the screen here while you write them on your paper. Okay. And then after you're done, match them with my answer. Three fundamental. How about I write P dot Q dot for physical quantities? All right. So now you know that my P dot Q dot stands for physical quantities in mechanics. So here's my list. The three fundamental physical quantities in mechanics. Did you get it to be mass, length, and time? Well, if you did, you're right. Next, let's do one thing. Let's list the SI units of these physical quantities. Now, I would like to emphasize that physics and chemistry, they are case-sensitive subjects. The case of the symbols, it matters. Like kilograms, the symbol for it is lowercase k, lowercase g. Okay, so this is your kilograms. Meter, lowercase m. Do not write uppercase M for meters. And lowercase s, the SI unit for time is seconds. Now, those of you who are thinking that, hey, she doesn't know how to spell meter, right? Meter is supposed to be M-E-T-R-E. You're right, but I'm not wrong either. M-E-T-R-E is the spelling for meter in British English. This is your British English, okay? And M-E-T-E-R is in American English. So use whichever you like, whichever is used wherever you live. Now, we have the SI units and the three fundamental physical quantities listed here. Next thing we're going to write down is the dimensional formula, okay? So I'm going to write DIM dot. This stands for dimensional, okay? Formula. Now, the dimensional formula will always open and end with square brackets. So I'm going to already put square brackets for all three of them. Next, we're going to look at how many factors of mass, of length, and of time are there in each quantity for which we are writing the dimensional formula. Okay, so there will be three things here. M, let me write all of them here. And the reason I want to do is because I like to color code my lectures, and it's hard to change colors every second. I'll tell you in a second what I mean. Okay, so first thing first, in the dimensional formula for mass, it is just for mass. We have only one mass. Okay, so you're going to write it m to the power 1. There's no length there, is there? We're writing the formula for mass, not for length, right? And nor for time. So here you go. So this M1L0T0 is the dimensional formula for mass. Next, moving on to length. Is there any mass in length? No, it is length. Is there any length in length? Duh. Yeah, we have one length in length. How about time? Nope. Because we're writing the dimensional formula for what? For length, not for time, not for mass. So the dimensional formula for length is M0L1T0. Okay. Lastly, for time, is there any mass in there? No. Is there any time in there? No. Is there any, sorry, if that was length. Is there any length in there? No. Is there any time in there? Yes, 1 unit of time. Okay, so now this is the dimensional formula. And using the dimensional formula, we determine the dimensions. Okay, it's there, cool desk. Now the dimensions are nothing but the powers. Okay, so write down all the three powers. 1, 0, 0. Correct? Just by looking at it, you should know that the first one is referring to mass. Second one is referring to length. Third one is referring to time. So there's 1 unit of mass here. So it is nothing but mass. Similarly, I'm sure by now you can figure out what the dimension of or what the dimensions of length would be. What do I write first? 1 or 0? Did I hear a 0? Good, you're right. Next, this is length. So we have 1 unit of length and 0 units of time. Let's put commas. Last is now for time. And for time, you have 0 units of mass, you have 0 units of length, and you have 1 unit of time. There you go. So here, okay, did not fit there. Now it fits here. There you go. So now we have written down the three fundamental physical quantities in mechanics. This is only in mechanics. We're not talking about electricity, magnetism here. We're not talking about temperature here, okay? This is, and also the luminous intensity. We're not talking about those things. But we will work on those formulae later. Not in this lecture, though, okay? Now, in this lecture, our goal for every other physical quantity will be, we're going to break down its physical dimensional formula into MLMT. Okay? Everything will be written down in terms of these basic fundamental quantities. Now let's generalize what we just learned. Generalize. The generalization would be, let's say you have any given physical quantity. Any physical quantity. Let's call it as P dot Q dot any general physical quantity, made up quantity. What do you want to call it? A. The dimensional formula for A would be, okay, first these square brackets around A. That tells you we're talking about the dimensional formula for A. Then when I'm writing the actual formula, then inside the parentheses, I should have M, L, and lastly, T. Now, I do not know the powers of these yet, but let's say the powers are here. A, B, and C. There are a number of factors of mass in the formula for A. There are B number of factors of L, and there are C numbers of factors of time in formula for A. What do I mean by that? You're going to see it as we move along this lecture. So this is the dimensional formula. Okay, I just do not like the way this generalized turned out to be because I wrote it and then I zoomed into it. Once you know the dimensional formula, can you figure out the dimensions of A? What will be the dimensions of A? What do you think? I say they would be what? What's the first one? A. Next we have B. And last we have C. So these are the dimensions of the physical quantity A, which is just some random made up fictitious physical quantity. Okay. So let's now apply what we have just learned to some actual physical quantities. Let's talk about speed. Everybody's familiar with speed, right? Speed is distance divided by time. Or even if we were talking about velocity, what is velocity? Velocity is, tell me, it is displacement divided by time. So let's say speed. You want to use U. U is for speed. Distance divided by time. And for velocity, we typically use V with an arrowhead over the letter B. And this arrowhead represents that V is a vector quantity. And delta X over delta T. What is delta X? That is the displacement. And just for those who might be interested, it might be XF minus XI. Final position minus the initial position. These are the position vectors, by the way. I don't expect this to make sense yet. If it doesn't, but we are going to get into all these things very soon. And when we work on these, I promise it will make sense. Divided by delta T, which is like final time minus initial time. And you can always take initial time to be 0 and final time to be just T. So instead of writing delta T, I can just write T. It's very common, customary to write it like this. What it means, again, I'll show you in a later chapter. But for now, as long as you understand that the formula for speed and velocity, they both have distance or displacement. That is these are the parameters containing length in the numerator. And in the denominator of both of these quantities, you have time. So next, let's see how we can get dimensions or dimensional formulae of u, which is speed, and v, which is velocity. So to get the dimensional formula for speed u, I'm going to write down the formula for u here. This is what I said the formula for u is. What do I want to determine? I want to figure out the dimensional formula. So to get that, to represent that you're talking about dimensional formula, what do? You write the quantity within the square brackets. And that's exactly what I did here on the left-hand side. So whatever you do to the left side, you have to do to the right side of the equation. Here you go. Correct? I know this looks pretty hideous actually. I guess I really cannot draw lines. So now this here, there are a bunch of ways to go around this thing. Let me show you them. You can say here that this is same as d times t to the power minus 1 here, right? You can leave it like this, or what you can do is then take this further and write this as, that's supposed to be green, here, d times t inverse, which can further be written as, first one is the d, second is the t, minus 1 comes out. So what's really happening is all these things are identical. Okay, you need to be able to understand that these are all the same things. Also, I could have written this as, so you could have gone this way, you could go this way, you could go straight from here to over here, from here to over here. I mean, do whatever makes sense to you. They will all lead to the same answer as long as it's done correctly. Alrighty, so I want to find out the dimensional formula for speed u. Which way do you want to do? Let's do this way here. I have D and T, dimensional formula for D times dimensional formula of T to the power minus 1. Okay. Dimensional formula for D, it is just length. That's all it is. And okay, how about I just use one color now just for the sake of time. MLT for D. Distance. Is there any mass? Nope, 0. Is there any length? Yes. Distance is length. Time. There's no time in D. 0. Parentheses closed. Next is for time. Any mass there? No. Any length there? No. Any time there? Yes. And this is raised to the power minus 1. Now, you could say that the previous dimensional formula is also raised to the power 1, but I'm sure you know that. You do not write that. Any number, if you write, you write 7, it is to the power 1. It's implied. It is understood. You do not write it, but that's what it actually is, correct? Also, it is multiplied by 1. It's divided by 1. All these things are implied. However, if instead of being raised to the power 1, if it was minus 1, now the meaning changes, right? Now you do have to write it down. That's all. This is I'm going to erase it here. Okie dokie. Next thing. This minus, 1, this power also comes inside, and outer power, outer exponent, it multiplies each of the inner exponents. But multiplication by 1 changes nothing, right? So this first dimensional formula stays as is. Cool. How about the second one now? Now the second one, minus 1, comes and multiplies each of the powers. And once again, 0 times anything is still 0. L to the power 0. But now t becomes t to the power minus 1. Okay. Taking it further. Now, if you have x to the power 2 times x to the power 1, what does this give you? X to the power 2 plus 1. Whenever you're multiplying any two variables, let's call them variables, as long as the base is same, which is x here, then when you're multiplying, what do? You add the powers. Same thing will apply here to our dimensional formulae. This dimensional formula for distance is multiplying the dimensional formula for time inverse. And in each of these, there are these symbols here now. They're not exactly variables, but they're still symbols. So you're going to apply the rules of algebra here now. So the first one becomes m to the power. What's the first one's power? 0. And second one's power is also 0. Then we have L to the power, this 1 plus this 0. T to the power 0 minus 1. What do we get? Let's close these parentheses. M0 L1 T minus 1. This is your dimensional formula for speed. But if you work out the dimensional formula for velocity, you will see that delta x, okay, I'll show you something here. I told you that delta x's final position minus initial position divided by t. So you will see that on the left hand side, I have this square brackets. Now, what do these square brackets represent? They represent that I'm talking about the dimensional formula for velocity. So if there's dimensional formula on the left side, then on the right side, I have to perform the same operation. So I'm going to just do like this. Cool so far? Up here I showed you that you're really doing this thing, but then that gives you this. So for the case of dimensional formula V, I went straight to this part here. Now, in the numerator here, on the right-hand side, how many terms are there? 1, 2. There are 2 vectors that are being subtracted. Okay. And we're taking the dimensional formula of that difference at the top in the numerator. So how do we do it? Okay. For this, there's very, very important concept. Let me write it down here. The principle of Homogeneity. Principle of homogeneity. What does it say? Homogeneity, well, homo, means same, uniform. So if you have an expression or an equation, so you're saying that for an expression or an equation, I write EQN dot for equation. The dimensions or the dimensional formula or the units. Okay. Dimensions, dimensional formula or units. All three of them. Of all the terms must be identical. Okay, now what does this mean? It means that for an expression, what's an expression? Expression will not have an equal sign. For example, if I write A plus B minus C, that's all. It could be, for instance, it could be 2x squared minus 3x plus 4. You know that this is a quadratic expression. Why? Because there is no equal sign here. So the moment I put an equal sign and put a 0 there on the right hand side, or anything else for the matter, it didn't have to be 0. I could have had 5x cubed. Now it's not quadratic, but now this is an equation. So an equation has an equal sign, while an expression does not have an equal sign. But nonetheless, what I'm about to say will apply to both of them. So let's say a plus b minus c could have been this thing. 2x squared minus 3x plus 4. A is 2x squared. B is minus 3x. And c here will be minus 4. Okay. Then the dimensions of each of them, dimensions or the dimensional formula for A equals dimensional formula for B equals dimensional formula for C. Why? Because I have three terms here. How come? Terms are separated by plus or minus signs. So see here, A is separated from B by a plus sign over here. B is separated from C by a minus sign. So there are three terms, T1, T2, T3. And all these, their dimensional formulae, therefore their dimensions are identical. Now also, okay, this 3 is really bad. Their units are also same. So the units of T1 equals units of T2 equals units of T3. That means if the units for quantity A were, let's say, newtons, that's the SI unit for force, or let's just make it meters, okay? Let's stick with what we know so far. Let's say the SI unit for quantity A, which is here, is meters. That means the quantity B and C must also have SI units of meters. Does that make sense? It will as we solve more problems. Okay, and similarly, if I had an equation A plus B minus C equals D minus E minus F. Okay, how many terms do we have now? Count with me. Terms are separated by pluses or minuses. So 1, 2, 3, 4, 5, 6. Now, because we have some terms on the right-hand side of the equation as well. So here's the T1 is A, T2 is B, T3 is C, T4 D, T5 E, T6 F. Now, by the way, I hope you do know what I mean by this T. T is just term. So when I say T1, I mean term 1. Just using shorthand here. So this is principle of homogeneity, and you will see several problems based on this very, very important principle. Back to this problem, where we're trying to determine the dimensional formula for velocity v. Okay, now we saw that when we're talking about multiplication or division, like here we were multiplying over here, then the rules were the simple, plain rules of algebra. When you're dividing, you bring it upstairs. See here, t, it had come upstairs. It was d over t. But I brought t up and changed its power to -1. It was +1 at the bottom, -1 when it comes to the top, to the numerator. So over here, now, when I'm talking about here, xf minus xi, how many terms do I have here? Term 1, term 2. They will both have same dimensions. Why? That's what principle of homogeneity tells us. So at the top, I will have only one-dimensional formula. I will not have two or three. In case of multiplication, division, you will see that it's different. If you're multiplying two quantities, A and B, then you will multiply their dimensional formulae, okay, like this. But if when you're adding or subtracting, the entire thing will have just one-dimensional formula, just one, okay? While here it will have one for A times the other for the B. And again, we're going to get into these things in very, very detail as this lesson progresses. So here, the B equals delta x over delta t, and I said delta x means xf minus xi, where the subscript f means final, subscript I means initial. And delta t should be tf minus ti, right? So what I'm saying is that ti equals 0. You start your clock, and at that time, your time counting starts. That's your initial time. And whatever the final time is, call it as t. Very, very customary to do it like this. Here's what we get then. Cool. Now to get the dimensional formula for B, I will write down the dimensional formula for xf minus xi divided by dimensional formula for t. Now the numerator will have dimensional formula for just length. Consider this as this is one whole expression here. An expression will have one dimensional formula. And for the case of length, it is m0, L1, T0. And then I have at the bottom, I have this time here, which is going to be m0, L0, T to the power 1. Now, this is plain algebra. You can do it any way you like to. Let me show you a couple of ways. You really do not have to make it complicated at all. I'll show you at the end how I would actually do it. This is the way to show you the complete work. But if I were to do it, I will do it a different way. Or I would just skip some of the steps, really. So this -1 in the second dimensional formula multiplies each of the exponents of, which is the exponent of m, l, and t. First one stays the same, m0, l1, t0. And the second one becomes m0, l0, t to the power -1. Very good. So this gives us m to the power 0, m to the power 0. Multiply this, m to the power 0 plus 0. L to the power 0 times L to the power, L to the power 1 here times L to the power 0, 1 plus 0. T to the power 0, T to the power -1. M0, L1, T minus 1. Same as the dimensional formula for speed. Oh, sorry, it wasn't fitting here. You should tell me. How would I know if you don't tell me? How are you going to tell me? I don't know that, but that's not my problem. Anyway, so here we got the dimensional formula for speed and velocity both. So knowing the dimensional formula, can you tell me what are the dimensions of them? Dimensions of speed or v, because they are same. So you write down the powers of the dimensional formula. You do not write m, l, or t. You write down just the powers in order. However, I have seen on some old JE published exams that they have kind of screwed up the order of M, L, and T. They are writing it as in the problem as L, M, T or T, M, L, whatever. So pay attention to the test. They like to mess up with you. So this is going to be 0, 1, minus 1. And if somebody comes to you and asks, hey, 0, 0, 1, minus 1, what are these dimensions of? And you will say these are dimensions of speed. Or if someone says 0, 1, minus 1 are the dimensions, write down the dimensional formula. M to the power 0, L to the power 1, T to the power minus 1, and we are done. So I hope it makes sense. This was very easy, very simple. Just the dimensional formula for speed and velocity. Next, we're going to talk about dimensional formula for acceleration. Let's now figure out the dimensional formula for acceleration. So dimensional formula for acceleration. Acceleration is represented by lowercase a. Like I said, you have to be careful about the case of the letter, of the symbol, because physics is case sensitive. Acceleration is always and always lowercase a. It's never uppercase a. And it's a vector quantity. On the right side, the formula says it is equal to delta v, change in velocity, divided by the time taken for the change in velocity to take place. So this is really Vf minus Vi divided by T. What do we want to do? We want to evaluate the dimensional formula for acceleration. That means we need this dimensional formula, which can be written like this. We have done it a couple of times already, and hopefully you get it by now. This we're going to write now. I'm going to just rewrite it a little bit. Vf minus Vi divided by T. Okay, we're writing yellow here. So we have already determined the dimensional formula for velocity, and that was m0 L1 T minus 1. Remember that? We just did it. Divided by dimensional formula for time, which is m0 L0 T1. So at this point now, it's up to you, however you want to do it. You can write this as m0 L1 T minus 1, m0 L0 T1. Okay. So I have brought this one upstairs and its sign has become -1 now. You could do this just fine. Or I mean, as long as you know basic algebra, you don't need to really do that. You know that m0 divided by m0. It's going to be m0 minus 0. This 0 minus this 0 here, correct? Then we have L to the power 1 minus the 0. Then we have T to the power this minus 1 divided by this T1. So this gives you this 1 becomes negative over here. This gives you m0 L1 T minus 2. You with me so far? Or, okay, or you could have brought this entire thing upstairs to the numerator and change the power of the entire dimensional formula. Then you know that this power, it goes and multiplies each of the powers on the inside of the parentheses. So this gives you, the first one doesn't change, right? And my bad, here, it's just a little bad writing here. This -1 was inside the parentheses, because if you put it outside, it changes the meaning. I mean, then that -1 will have to come inside the parentheses and multiply each of the powers, like we're doing over here. But that would give us a wrong answer. And I hope that you can see that how. m0 L1 T minus 1. And the next one becomes m0 L0 T minus 1. Now, after this, m0 times m0 gives you what? M to the power 0 plus 0. Then we have this L to the power 1 times this L to the power 0 gives you L to the power 1 plus 0. Then we have the last one is t to the power minus 1, and this minus 1. What do we get? M to the power 0, L to the power 1, T to the power minus 2, just like over here. Same thing. However you want to do it, you can do it. If I were to do it, what would I do? I would like to do it this way here. I mean, it's just so much easier, right? Actually, I might even do something different here. I'll show you what I would actually do. If I were taking this test and it was a multiple choice question, then I know that I don't get any points for showing my work. So, and as long as I'm confident in my knowledge here, I will take shortcuts. So I know that this is delta V over delta T. I know that velocity is just distance over time, or sorry, displacement over time. So that is L1T minus 1. I know that M is 0 for delta V. I wouldn't even write it. What's the point of writing it for now? And delta T, I will just write T here. Okay. So technically, this is not correct. Let me just put this equivalent signs here. So technically, it is incorrect, but as long as it makes sense to you, it's going in your head, you could definitely do this. So this will then give you L to the power 1, and this T to the 1 comes upstairs and becomes T to the negative 1, and combines with this T to the negative 1. Together becomes T to the minus 2. But like we know, we have to write M, but there is no M, so it has to be M to the power 0. There. So this is kind of like intermediate step that is technically incorrect. Technically incorrect. But hey, if it makes sense to you, it makes sense to you. You're not showing your work to anybody. All you're interested in is in the final answer, and you got it. Got it for acceleration? The next logical step after acceleration will be something, a physical quantity that uses acceleration, right? So according to Newton's second law, what is Newton's second law? It says force F equals mass times acceleration. Okay? Force equals mass times acceleration. Find out the dimensional formula for mass. Find out the dimensional formula for force. I misspoke. Here we go. So on the right hand side, write down the parentheses. Now, I'll show you technically how it should be done. And then at the end, I'll show you how I would do it if I were under some time crunch, or if I were taking a test in which it was a multiple choice question and I don't need to show my work, what I would do then. For now though, I will write it as dimensional formula for M times dimensional formula for A. All right. So dimensional formula for M is M0, not 0, M1. So dimensional formula for M is M1 L0 T0. And the dimensional formula for A is, we just derived it, M0 L1 T minus 2. Now, just like before, these two factors with the base of M, they multiply, giving you M to the power 0 plus 0, sorry, and this gives you M to the power 1 plus 0, L to the power 0 plus 1, T to the power 0 minus 2. What do we get? M1 L1 T minus 2. This is the dimensional formula for force. This is a very, very important dimensional formula. You might feel tempted to memorize this. Might be a useful thing to do. However, as long as you remember that force is mass times acceleration, and like here. So here's what I would do. I do not memorize things. Maybe I just have a weakness where I have a hard time memorizing things, especially if I want to memorize them. If I don't want to remember things, I'll remember them for the rest of my life. But if I intentionally want to remember something, I'll forget it the next second. So that's my problem. Hopefully, you do not have the same problem. Excuse me. So here's what I would do if I were under time crunch. So here for M, I would write just M1. That's all there is in M, mass. It's just one mass. No length, no time. Leave it there. Next, acceleration. I just know it is L1 t minus 2 because acceleration was m0 L1 t minus 2. So m to the 0, I do not need to write it. Here, done. That's as long as it takes to do it. All you need to do is remember one thing, force equals mass times acceleration. And honestly, as long as you study this physics course even half seriously, you should remember that force equals mass times acceleration. Because when we get to the chapter on Newton's laws of motion, you're going to solve an insane number of problems on Newton's second law. I mean, in every problem, you will use F equals ma, F equals ma. There's just no way you're not going to remember it. You'll remember it. If I remember it, you will remember it. Okay, so the way I'm trying to build this is that whatever I have derived, I want to utilize this to figure out the next thing, and so on. So I don't want to get into the details, but work is defined as force times distance or displacement times cosine of angle theta between F and D. Okay. Theta is between F and D. What does this mean? Don't worry about this yet. Again, there will be a complete chapter devoted to this, and you're going to learn this in great detail there. But before I work out the dimensional formula for work, I want to introduce one more physical quantity, energy. It is defined as the ability to perform work, to do work. So in terms of the units and dimensional formula, it turns out that the energy and work have the same dimensional formula and therefore the same units. And in terms of SI units, the energy and work, they both have SI unit of joules. And once again, I'm kind of jumping ahead of myself here. We don't need to do this, but just to let you know for those who are want to learn a little more. Okay, so I know that energy and work have the same dimensional formulae. Okay, now energy, let's talk about energy for a second. How many kinds of energies are you familiar with? You know that it could be kinetic energy, right? It could be gravitational potential energy. You could have spring energy. So there's solar energy, which is really nuclear energy. Then we have wind energy. We have geothermal energy. All these different kinds of energies. Let's just stick with kinetic energy or gravitational potential energy for now. Kinetic energy, do you know it's 1/2 mv squared, the formula? Hopefully you do know that. And gravitational potential energy is mgh, where g is acceleration due to gravity. Okay. Very normally people will write acc dot, which means acceleration due to gravity. And h is the height above the ground or height above the reference level. Okay. Okay. So we know that whatever the dimensional formula for kinetic energy is, that should be the same as gravitational potential energy because these are just energies. Should be same as that of work. Okay. So let's see what we can find out of this thing. What does this tell us? Kinetic energy is 1/2 mv squared, right? Then I'm going to write gravitational potential energy is mgh. Okay. Then lastly, I have work. Let me write work as, I don't want to use blue here. I want to use pink color. or I could have used green. Work with force times displacement times cosine theta. All right. So now I'm going to write this one as dimensional formula for 1/2 times dimensional formula for mass times dimensional formula for, I could just say V squared, or I could close the parentheses and write square outside. It doesn't matter. MGH. Okay. Mass GH. Okay. And the last. With me so far? So what I will do is the easiest of these, well, they're all easy actually, if you know it. I'm going to find out this first. Then I'll equate with the 1/2 mv squared and with FD cosine theta individually. And from that, I can show you, first, we'll figure out the dimensional formula for energy, that is of work, and then I will show you what the dimensional formula for 1/2 is and what the dimensional formula for cosine theta is. I want to show that to you. So MGH. First one M. M1 L0 T0. G is just acceleration. Acceleration is M0 L1 T minus 2. H is height. Okay. Height is M0 L1 T0. Now go ahead and multiply M1 times M0 times M0 gives you M to the power 1 plus 0 plus 0. Then I have, okay, L. L to the power 0 plus 1 plus 1. Last. Okay. Lastly, I have T. T to the power 0 minus 2 plus 0. What does this give me? M to the power 1, L to the power 2, T to the power minus 2. So this is MGH here. Did I really need to do all this? Nah. I could have just started over here and said mass, it's just mass here. Then I have G. G is L1T minus 2. Then I have H. H is just L. Combine these together and you will get M1, this is 1, L times L, L2, and T minus 2. So here I have the dimensional formula for gravitational potential energy. Now, what did I say this is equal to? This is energy, all kinds of energy, no matter what they are. The dimensional formulae are all identical. M1, L2, T minus 2. And the dimensions are 1, 2, minus 2. Just write down the exponents. Now, I do know that the gravitational potential energies dimensional formula is same as that of kinetic energies, right? So I know that on the left-hand side, I have M1 L2 T minus 2. On the right-hand side, I have this 1/2. How about I just write M for M, and for V squared, I'm going to write L squared minus T squared. Why? Because V is M0 L1 T minus 1. So V squared will be M0 L2 T minus 2, but M0, I'm just not writing it, just to make my life easy. All right, so now look at this. I want to find this dimensional formula, 1/2. But it is multiplying this M1 L2 T minus 2. So divide both sides by M1 L2 T minus 2. Cancelled out on the right hand side, but look here. It cancelled out even on the left hand side. So what does this give us? 1/2 dimensional formula is nothing. It's really M0 L0 T0. How? Because, hey, take this upstairs. It becomes what? So we have M1 L2 T minus 2 up there. right? And when you bring the bottom one up, it becomes m1 L2 t minus 2 to the power negative 1. The negative 1 goes inside and becomes m minus 1 L minus 2t plus 2. Now multiply these together. M1, m minus 1, 1 minus 1. L2, t, L minus 2, t minus 2, t plus 2 equals m0, L0, t0. So 1/2 is dimensionless. We call such quantities as dimensionless quantities. So this was just for 1/2. What is 1/2? 1/2 is a constant number. So any constant, no matter what it is, million, 10,000, minus 50, whatever it is, any constant number, it's just a number. It will not have any dimensions. Its dimensions are m0, L0, t0. In other words, it's dimensionless. I hope that's clear. Then we had, other thing was, we had GPE, we said is also equal to the dimensional formula for work. Okay, here. This is what we were talking about over here. See, right here. Then we said that work equals FD cosine theta. So I'm going to write this as FD cosine theta. From here, I want to find out the dimensional formula for cosine theta because forces dimensional formula, I know it. I figured it out earlier in this lecture. D is just distance, it's just length. So I can write this as F, D, and cosine theta. Okay, force are now is M1, L1, T minus 2. Then I have this D. D is M0, L1, T0. Times. Look, dimensional formula for cosine theta. Alrighty. On the left-hand side, I have M1, L2, T minus 2. We have already done this thing. See, right here. 1, 2 minus 2. So I'm just putting that in here. Now on the right-hand side, M1 times M0 gives you M1. L1 times L1 gives you L2. T minus 2 times T0 gives you T minus 2 times cosine theta equals M1 L2 T minus 2. Now, in the previous one, I had similar thing here, see? I had M1 L2 T minus 2 here and over here, and I divided both sides by the same factor. Why? Because really, I was trying to isolate 1/2. I was trying to get rid of anything that's multiplying or dividing 1/2. So I have just 1/2 by itself on one side of the equation. So to do the same thing over here, I want to isolate this dimensional formula for cosine theta. I really need to technically divide both sides by M1 L2 T minus 2. But look here, I have same thing on both sides. Sure, if you are taking the test and you're supposed to expect it to show all your steps, by all means, show that you're dividing both sides by M1 L2 T minus 2. But if it's a multiple choice, you look at it and you see it. It is M0 L0 T0. That cosine theta is dimensionless quantity. Now why? Think about it. Just think. Cosine 0 degrees, 1. Cosine 45 degrees, square root 2 over 2. Cosine 90 degrees is 0. What are all these things? These are constant numbers, correct? And just here we said that the constant numbers are dimensionless. So same thing for sine of any angle, same thing for tangent of any angle, or cosecant, or secant, or what's the last one? Cotangent. So trigonometric functions, all trigonometric functions are what? Dimensionless. That means you may have sine theta is dimensions. Cos theta could be whatever the angle might be. Tangent theta. These are all M0, L0, T0. Now, of course, if sine theta is dimensionless, then what would be cosecant theta? Dimensionless, because it's inverse of sine theta. If cosecant theta is, sorry, if cosine is dimensionless, then secant will be dimensionless. If tangent is dimensionless, then cotangent will be dimensionless as well. So this is an important point that you want to make a note of. That so first one was all constant numbers are dimensionless. Second, we did all trigonometric functions are dimensionless. This is not it. What else is dimensionless? Um, if you're taking exponential of something, right? You could have exponential whatever, kx. Then this is going to give you some kind of number. Okay, and number, constant number, is always dimensionless. So anytime you're taking exponential of whatever, this is going to be a dimensionless quantity. And that was one thing. And this argument, kx is the argument here. And okay, argument. Kx is the argument. So again, exponentials, dimensionless. Not just that, even the argument will be dimensionless because the argument needs to be a number. Whatever this kx is here, kx minus kx, whatever I write. When you do the wave equations, you're going to learn that x is the distance and k is the wave number. Okay, and together the SI unit for k is 1 over meter and for x is meter. So the units cancel out. So if the units cancel out, that means the physical dimensions, that the dimensional formulae, the dimensions also cancel out. What else is dimensionless? Logs. Log of anything. Again, this argument will be dimensionless because it needs to be a number. All the units must cancel out. And this entire thing will be dimensionless as well. So here's another thing. And one more. Any number to the power of any number. This will be dimensionless. This will be dimensionless. And this whole thing will be dimensionless as well. For example, if I'm writing 7 to the power of something, I may have some variables over here, but they are all going to cancel out in such a way that at the end it will be dimensionless. And over here it is 7 to the power something, right? It cannot be 7 to the power 5 meters. That doesn't make any sense. It could be 7 to the power 5. It could be 7 to the power 7. But I can't say 7 to the power 8 seconds. This means nothing, physically speaking. So here I gave you a list of the dimensionless things. I'll also give you a list of the dimensionless physical quantities. Constant numbers, trig functions. I know I'm writing shorthands here, but hey, you're taking physics, get used to writing in shortcuts. But I'm saying every word, so you should be hearing me, you should be listening to me, and you should know what I'm talking about here. Exponential functions, log functions, powers. Okay, cool. So we have figured out the dimensional formulae of quite a few physical quantities so far, and I'm going to work out several problems in the upcoming lectures, but now I want to get into why do all this? What's the point of doing all this? Let's look at that. Let's have a quick review of what we have learned so far. To represent the dimensional formula of any physical quantity A, you put square parentheses around it. And in mechanics, the physical dimensional formula will have three factors here, m, l, and t. That will be raised to the power A, B, and C. These powers tell you, for instance, m is contained, multiplied by itself a number of times. L in the formula for A is multiplied by itself B number of times, and T is multiplied by itself C number of times. For example, with force is M1, L1, T minus 2. So whatever the formula for force was, which we said was mass times acceleration, so we broke this down into the ultimate building blocks, which are M, L, and T. These M, L, and T, mass, length, and time, these are the fundamental, the base of fundamental physical quantities. So M, L, and T, these are the base, also called as the fundamental physical quantities in mechanics. So every physical quantity will be written in terms of these three. Okay, after this, we talked about the operations that can be performed on two or more dimensional formulae. For example, if you're multiplying two different dimensional formulae, A, dimensional formula of A times the dimensional formula for B, how would we do it? You will write down the dimensional formula for A. Let's say it is m to the power A, L to the power B, T to the power C. And B is m to the power D, L to the power E, and T to the power F. Then what do? You're going to multiply these two, okay? What does this give us? M to the power A plus D. Then we have this L to the power B times this L to the power E. Okay. Lastly, we have T to the power C times T to the power F. So whenever the base is same, what do? You add up the powers. So if I had a third physical quantity with it, let's say I had, let's say, divided by C, okay? And what is C? Let's put it like this. C, make it M, L, N, and last is T to the power P, right? So this will come upstairs, correct? It will come to the numerator, and it will become M to the power M, L to the power N, T to the power P, this to the power -1. Sorry. And this -1 is going to multiply each of these powers. So instead of writing this, I could have straight away wrote m to the power -m, L to the power -n, T to the power -p. So whenever you bring something like from denominator to numerator or vice versa, you will switch the signs of the powers. That's all you have to do. And over here, what do we have? M to the power A plus D, L to the power B plus E, T to the power C plus F. Now this becomes what? M to the power A plus D minus this M. L to the power B plus E minus N. T to the power, this is not plus, this is T. All right, I'll rewrite it. T to the power C plus F minus P. Put your square parentheses. That's it. So what is it? It's just simple plain algebra that I hope you already know how to do. Okay. If for some reason you do not remember the basic rules of operations of algebra, I suggest that you review those first. Okay, so that was that. If you're multiplying or dividing two or more physical dimensional formulae, you're going to solve this. You're going to get the final answer, final dimensional formula. You're going to get that using the rules of simple plain algebra. Got it. Next thing, very important, okay, star, is the principle of homogeneity. Let me show you first how it works. Okay. So I bet you are familiar with the formula delta x equals v naught t plus 1/2 at squared, correct? This is the one of the equations of motion, right? So delta x on the left hand side, this is your displacement, correct? V naught, initial velocity, t time a acceleration. So here, delta x, all right, you can put a vector notation here if you would like. Here v naught is vector and here a is vector. This is displacement. And when I write delta x, it's along x-axis. V naught, initial velocity. This zero here, it's called as naught. It sounds as like N-O-T, but I think it's is acceleration. Very cool. All right, so what does principle of homogeneity says? It says that, let's rewrite the equation, delta x equals v naught t plus 1/2 at squared. How many terms are there? Here's one term, call it t1. This is t2, and this here is t3. So principle of homogeneity says, you could say it in one of the two ways, that the dimensions of each of these terms is identical, or their units are the same. Unit of the term t1 equals the unit of the t2, unit of t3. So how about we check out the units first? Because why? Because that's really easy. Delta x, units. Let me have some water. Delta x, SI units. Meters, lowercase m. V naught t, V naught, velocity, meters per second, times t, seconds. Seconds cancel out, you're left with meters. 1/2 at squared, the last term. 1/2, it's unitless, it's just a number. Acceleration a, meters per second squared. T squared, t is seconds, and it's being squared, squared. S squared canceled out, you're left with meters. So there, the SI unit for each of the three terms in this equation is the same. Okay, so this is one way to check that the equation is correct. Okay, so the principle of homogeneity, we know what it is, but the importance of it is that if you're given an equation, how do you know it is correct? There's one thing you will check. For an equation or even an expression to be physically consistent, that means it has to make physical sense. It needs to be correct, physically consistent. It must be dimensionally consistent. Physically, it is correct only if the dimensions of each of the terms is identical. So this is a necessary condition for an equation to be correct. If it is dimensionally inconsistent, that means the dimensions of one term is different from the dimension of the second, and so on, then that equation is definitely wrong. Okay, this is a necessary condition for an equation to be correct. Is it a sufficient condition? Just because a given equation or an expression is dimensionally consistent, that means the dimensions of each of the terms is the same. Is the equation or the expression correct? Not necessarily. So it is a necessary but not sufficient condition. So if you have done math, then you will learn about this way of proving or making statements that blah blah is a necessary but not sufficient condition for some theorem to be correct. or you can say that this is necessary and sufficient condition. Okay, so principle of homogeneity, it is a necessary, the principle of homogeneity must hold true, okay, for an equation to be correct. But just because the principle of homogeneity is true for a given equation does not mean that the equation is physically correct. It could still be a wrong equation. For example, if I wrote, let's see an example of when an equation can be dimensionally correct, but it is actually an incorrect equation. Let's say delta x equals, okay, I write really bad delta, v naught squared divided by a. Let's see if this equation is dimensionally correct. If it's dimensionally correct, then on the left-hand side, we should have units of meters. And the units on the right-hand side should also reduce to be meters on the right-hand side. And the units on the right-hand side should also reduce down to meters. So V naught square should be meter square or second square divided by A. A is, let's pull it up, meter over second squared. So here, second square cancels second squared, and one of the meters cancels, one of the meters at the top cancels one of the meters at the bottom, leaving you with meters. So here meters equals meters. So dimensionally consistent. Why is it not right equation? There's this equation, v squared equals v naught squared plus 2a delta x. So in this equation, this is again one of the equations of motion. We are saying if we make this v squared equals 0, then we will get delta x to be minus v naught squared over 2a. So yeah, this equation is dimensionally correct, but you can see that there's this negative sign missing and this factor of 1/2 is missing. Let's look at some other example of how this principle of homogeneity can be useful to solve problems. Let's say you're given a problem, 2ft over m equal plus a equals 0. Okay, so we're given this thing, given this equation where F is force, right? F is force, T is time, just the regular usual things. M is mass. And you're asked to find out the dimensions of A, or just the units of A, or just dimensions of A. So this is dimensional formula here. These are just units. And using the dimensional formula, you can find out the units. All right, how would you do it? Using the principle of homogeneity, you know that the units of 2ft over m must be the same as A. You could equate the units, and from there you could figure out the units of A. Or you could equate the dimensions. So you could say that dimension of 2ft over m, this dimension equals dimension of A. This is principle of homogeneity. 2 here is dimensionless, so just take it out. F, let's make this yellow. F is m1 L1 t minus 2. Then I have t. This t is just 1t. Then I have m at the bottom, which gives me m here. And this m is to the power 1. So there you go. M1 cancels out M1, and you're left with L1 to the power t to the power minus 1 equals dimensional formula for A, which, to be technically correct, you have to write M0 L1 t minus 1 is A. And just by looking at this, can you tell me what physical quantity it is? There's no mass. There's length at the top, time at the bottom, correct? It could be speed or velocity. Did you want to solve it using units? Yes, you could. Here, let's do it. On the left-hand side, F, I would write F as mass times acceleration. Then I have T divided by M. So here this M's cancel out. I'm left with A times T. A is meters per second squared times this T, the units are seconds. One of the seconds at the top cancels one of the seconds at the bottom, and you're left with meters per second. And if it's meters per second, means there's no mass, m to the 0, meters at the top, l to the power 1, seconds at the bottom, t to the power minus 1. So this is, the dimensions are 0, 1, minus 1, dimensional formula, dimensions, and units. Here we got them all. What else did I want to cover in this lecture? Yeah, one more very, very important thing. So you just saw me use units and dimensions both to solve the problem, the previous problem that I just wrote down. And we could really use them both, but is there any physical quantity? Okay, is there a physical quantity with units but no dimensions? What do you think? And another question I want to ask you is there a physical quantity with dimensions but no units? Okay, so the first one, the answer is, what do you think the answer for the first one is? Here's your question, here's your answer. Yes, there is one and only one physical quantity that has units but no dimensions. And that's going to be angular displacement. So when something moves around in a circle, okay, I can show it to you actually. Like this, say, I'll write 1,000 words because a picture is worth 1,000 words. Is this a good enough circle for you guys? Good enough for me. I know it's not the best, and I can see that this is over here not completed. So, but you do know that we start measuring angle with respect to the 0 degrees along the positive x-axis. So let's say you have a ball or any object connected to a string. You're holding the string over here and you whirl it around in a circle like this. Okay. So this ball here, it's moving, and in certain time t, it goes from 0 degrees to over here. And this is the angle traveled, theta. This theta is measured in, you can say delta theta or theta in radians. So radians are the SI units for the angular displacement, but it does not have any dimensions, 0 dimensions. So that is two-dimensional angular displacement. Then we have the 3D angle, 3D angular displacement. Okay. One more shorthand, ANG dot, angular. Measured in steradians. What does the 3D angle mean? 3D displacement means? 3D angle we'll talk about some other time, but just to understand it, you could think of it like a cone, like the projection of a cone. So how would you build a cone? Something like this. Okay. So if you have a three-dimensional object like this at the bottom here, you project its ends up here, this angle that will be measured in 3 dimensions. Okay, that's pretty bad. It was hiding behind me. This angle, it will be steradians. We don't need to do this here yet, but just to answer this question, angular displacement. Whenever you're measuring angle, there are units, radians to radians, no dimensions. But if you're asked question, is there any physical quantity that has dimensions but no units? Answer is no. There's no physical quantity with no dimensions that will have a unit. So it's true one way, but not true the other way. There are physical quantities that have units but no dimensions. Angle. There is no quantity that has no dimension but has a unit.